he was my batchmate, so we know each other rather well. He did his PhD from the University of Delaware, after which he joined uh, ExxonMobil as senior engineer. You can see from the thing. What he did his PhD in is process control, something we are not all that comfortable with. But it is a really lucrative field. Not many people know how to do it well, and there's a huge demand for it. So listen carefully, and maybe one of you might follow this career. Okay, Swat, please. Thank you. Take the mic.
Vishwanath. And I'd also like to thank Transborder Educators for giving me this opportunity to speak with all of you. I know it's exam week for many of you there, so from my experience in ICT, it's very thick, and I appreciate that you are still here to listen to my talk. Um, Next slide. There. Okay, so I started my engineering journey back in 1998 when I joined ICT. It was called UDCT at that time. I was really clueless about engineering, knew nothing about it. And then I started learning more about chemical engineering, liked it, and I had opportunity to listen to many of the seminars like today. And some of them were informative, I could understand, and some of them went over my head. Um, Hopefully, this is not the one of. After that, I did my PhD in chemical engineering, as Dr. Vishwanath said, in process control. I'll be talking a little bit about that. And now I'm a process control and optimization engineer at ExxonMobil. Give a brief outline talk. We'll discuss a little bit about background of process control, and we'll talk about process control applications. Just a brief overview. I'm not gonna go in the theory of how it's done, but just to give you an idea of what applications are out there in the industry. And we'll talk about basic regulatory control, single variable, multivariable control, and finally real-time optimization, which is the field I'm currently working in. This is by no means intended to be a very comprehensive list of applications. It's just what I have seen while working in the industry. We'll move on. Next one. So are you ready for some advanced process control? It appears that the job of a process control engineer will be very cool. You're working with applications all the time, and you can watch football on the side, as the cartoon shows. But it's also really a very critical job in the plant. You have to concentrate because any mistake you do can be dangerous and critical to the safe operation of the. So that we'll just go in a little bit of background of how a process control application started in 1950s, and at that time it was all manual control, meaning somebody would look at the sensors and see how the reading was. It would manually change the valve as shown in this cartoon here. You see the man in the cartoon is smiling, but that's not usually the case. It's very a hot and very difficult place to work, and operators don't appreciate having to go out and manually move the valves. And imagine there are hundreds, if not thousands, of process control loops out there, and if every one loop there's an operator that needs to be looking at, it's very safe. So the manual control typically led to the development of more automated control schemes. And with time, we can see in this what I'm showing you is the number of fatal injuries um, and how they have trended over the last couple of decades. This graph was put forth by OSHA, which stands for Occupational Safety and Health Administration, and it is put in regulations and controls to reduce the workplace injuries. Over time, the number of fatal injuries have gone down considerably. Now, for each fatal injury, there are many more minor injuries that happen inside a plant. So you can see that due to the regulations being put forth and the controls that have been put in place, the number of injuries have gone down over the year. And that's the value of process control to a operational unit. So how does the transition from manual control to automatic control happen over the year? Well, there were many developments that happened, and one of the primary ones was in the field of uh, instrumentation, where the instruments were able to make readings accurately as well as send them to the distributed control network for um, for the auto controls, as well as the other important development was the um, control element, which is usually a valve. In this case, the change was from a manually controlled to a pneumatic or automatic um, or a motor-driven control valve. Here in the picture below, I'm showing a pneumatic control valve. What it does, it uses air pressure to move a diaphragm that controls the opening of the valve. What this allowed us to do is remotely control the flow through different units as well as implement more complex control schemes. So we have a controller. Um, we will talk about it a little more. User interface. How do operators view the controller is very important. If they don't really understand, then the controller is not very useful. And so are the work processes. Work process means when do operators use a particular control scheme, when do they turn it off, and there are guidelines for them to properly use a controller, and that's what is very critical for the operation or a success of a control scheme. Okay. So what are the key considerations that you have to take into account building a control scheme? First of all, as we talked about, the safety. Safe operation is critical. You want to build a control which is safe. Um, Nowadays, people are very conscious about environmental emissions from refineries and chemical plants too. And you want to make sure that you meet uh, all the set controls or the limits for the emissions. So you want a controller that is easy to operate for the operators. If it's very tedious, they're likely not use it. So you want to have a very easy to operate controller. Sometimes the controllers are designed to meet the product specs, and they can also be used for improving the profitability of a unit. So, I think I'm missing a slide here. Oh, yeah. Well, we'll talk about single variable control. But before I go into single level control, there's a layer beneath that. It is the basic regulatory controls. The basic regulatory controls are out there in the field, close to the process, and they are usually temperature, pressure, or flow control loops. And what they do is essentially when you set a set point for a flow control, this basic controller achieves the set point and keeps the flow at the value that you want. These basic control loops are the base of the pyramid. If the instrumentation in a refinery is not good and the basic controllers are not working properly, all bets are off. All other success of any other advanced control scheme will depend on how well this basic controllers perform. So it's very essential to have good instrumentation. From my experience working in the chemical industry, the refineries have been built long time back, many of them in 1950s or 60s, and then they do not have a proper instrumentation. As a result, it's very difficult to implement advanced control schemes with a poor instrumentation. So the first thing when we go in doing a project is to tell the refineries the instrumentation issues. So if you have your instrumentation issues fixed and you have basic regulatory controllers working properly, now you can do a little bit of advanced stuff, and that includes a single variable control. We'll talk about applications in two fields here. Single loop control, you're using one controller for here for controlling a single variable, and there's a cascade control loop where you are using two different loops to control a single variable. Just to give a representation of a single control loop, here we are trying to control a level of the tank using the bottom, and all the control is doing is getting the leveling from the sensor and then setting a set point for the valve. Very simple control scheme. Looks like it needs instrumentation to be able to provide this set point here, and then also the level sensor here as well as the controller design. There are many applications of the single loop control, and one of the primary applications that you will see a lot in a refining or a chemical plant is surge tank control or the level control in general. What's the importance of a feed surge tank level control? It's the level of the tank that feeds to the unit. If this controller doesn't work properly, then the feed to the unit starts swinging and never have a stable operations. The operators get mad at you if they find that the controller is not working and causing them more headaches in operation. Tower bottoms level control is critical because if the bottom level goes high, it leads to flooding. If it goes too low, then the trays are getting drier. Either of the situation is not very good. So if the instrumentation or the level reading goes out of the operator view for some reason, some instrumentation reason or wiring reasons, there is an operator that needs to stand out and just see that what the actual level is, and tell the operator on the board make the necessary corrections to control it, because it's one of the critical levels in the unit. Sometimes when the level goes out for extended time, it may lead to a shutdown of the entire unit. After that, the overhead receiver level those are also doing a simple level control, but they are maintaining a steady flow to the downstream units. If they don't properly, and if there's a big swing in the feed going to the downstream units, then um, then the operator on the other boards are gonna come after you. You really don't want that. So you want those level controllers to be working real well. Um, Tower overhead temperature controllers are usually used for determining the efficiency of the distillation. If the temperature, essentially what you do using this temperature is set the cut point for the overhead stream, and it's again critical to meeting the product specs. And so is the tower overhead pressure control. All right. Um, I think we're missing a slide here that was on Cascade Control, but all right. PID as a single loop controller. Now, most of these applications PID as a single loop controller, and it has been used for more than half a century in the refining industry. In fact, the first application was about 100 years back, um, and it was steering sheep, according to Wikipedia. You can read more about it on the wiki. Um, there have been more than 200 better alternatives. When I was working on my thesis at University of Delaware, my professor was working on an alternative to PID, which definitely looked better. But these alternatives are rarely used in the chemical industry. The reason being the chemical plants or the refineries have been built in 1950s and 60s, have pretty old instrumentation, and now to change all that and replace it with a better PID controller will cost the refineries millions of dollars. And really, I mean, the PID controller works. It doesn't work real good, but it works for reasonably well for the purposes it's used for. So why fix it if it ain't broke attitude is there? So you will find PID controller that we learn in our graduate class to be very commonly used in the industry. Right. Cascade control loop has two controllers, and there are actually two loops, the primary and one is the secondary loop. And the reason we use the cascade structure is that we do not want the disturbances in the secondary loop to affect um, control the control variable in the primary loop. In this example, the temperature is our critical variable. We want to match the temperature as best as we can. We do not want the disturbances coming in the flow of the reactants to affect that temperature. So we have this secondary loop that does uh, changes the steam flow to compensate for the disturbances in the reactant flow mixture. Now, where this is useful in the chemical industry is for furnace control, especially in the refining industry. Um, a furnace is like a gas stove, but only about 1,000 times bigger. It uses fuel gas to heat up the process fluids that pass through it, and it's a tall structure. You can identify a furnace from a distance usually. Uh, the main objectives here is to maintain proper rate of heat energy to the charge. Um, you set the temperature, coil outlet temperature for the process fluid, and you change the fuel gas um, that's been provided to the to achieve that temperature. So it's a kind of a cascade control loop that we use. Um, One of the other main objective is to maintain proper to fuel ratio. If the air to fuel ratio goes low and you have lot of fuel gas in your furnace, then it's a dangerous situation. Your furnace starts shaking. This situation is called flooding, and entire furnace has become a bomb which has fuel gas in it. If it finds a ignition source and if this furnace explodes, it's gonna destroy many units, nearby units, and probably cause many injuries around the plant. So anytime the furnace are shaking, we always used to get an instruction to run away from it, because if you stay around there and if something happens, you are in the target of possible damage. So to maintain that air to fuel ratio properly, you need to have a very good cascade control scheme that can do it for you. Also, emissions can be kept below the environmentally safe limits if you have a good cascade control. So you'll find the cascade controllers also pretty prevalent in refining and chemical industry, and they are used for um, very important purpose such as furnace controls. There's some very well-known limitations of the basic controllers. One of the main limitations is there can be, if you want to do multi-loop control for controlling many variables at the same time, you would have issues with the complex structures that you build. So how implementing those complex structures will be very difficult because instrumentation or the DCS system may not support it. It is also well known that the interactions between two or more controllers can quickly cause a drop in efficiency of the control scheme. As we have learned in our undergraduate course, that if there are two or more controllers and if the relative gain is high, then it's very difficult to control those two loops independently. Uh, Basic controllers do not do a real good job if there are time delays or non-linearities in the system. So they have many important applications, but we need something else beyond that. And that's what the multivariable controllers address. These are multivariable controllers are typically built for systems with more than two MVs. By MVs I mean the manipulatables, and two CVs, the control variables. There are many commercial tools available in the market to do this. One of the couple of the tools that I have used in my work is Aspen One, DMC, and Honeywell Profit Controllers. And both these tools use the model predictive control techniques, which are now pretty well known in the control community. What's a model predictive control is? Um, Model predictive control, as the name suggests, uses the model to um, see how the process will behave in future, and essentially the models becomes the eyes of this controller, and because it can see in the future, it can make smarter decisions. Usually these controllers are implemented remotely on a server, which can do the advanced computations that it requires at a very fast rate. We'll talk a little bit about the dynamic matrix control. I have used this frequently in my work, and it's one of the mature model predictive control technologies out there. It was started by Charles Kettler. If you work in the field of process control, you will hear this name sooner or later. He started DMC Core in 1984. He's one of the well-known experts in the field. Actually, the idea to build a DMC controller came to him much before. He was working on a project in Shell Oil Company in 1960s and 70s to optimize a fluid catalytic cracking unit. And he realized the targets of his controller or optimizer, he needs a controller that can accept the targets and implement them at the unit level. So he essentially needed a multivariable controller to implement the optimization targets, and that was how the C idea got started. C Corporation was acquired by AspenTech in 1999, and it was one of the major acquisitions for AspenTech. And now this Aspen One DMC product is being used by many companies worldwide. So what this controller has multiple inputs and multiple outputs, as we talked about. It's a bit complex to build. It can take a few months to a year to build a DMC controller for a unit. But the advantage is it can handle variety of constraints, can be process constraints or anything that you want your unit to be constrained due to safety, environmental reasons. You can put those constraints in the DMC controller, and it usually does a good job of handling those. Yeah, there are large applications out there, especially in the chemical field, um, which can handle more than 25 MVs. So it can move 25 valves out in the field for you, and it can handle over 100 constraints. So you can see it's a pretty big application compared to your simple regulatory controllers. And typically you would have one application per unit. You do not want too many because the operators usually won't like having to babysit too many applications. And one of the things that's critical to its success is the feedback from the operators. If the operators don't like it, the DMC application will be turned off very soon. So one of the key things in the success of a DMC controller is to get the operators involved right from the designing stage all the way to the implementation stage. That way they are always in, and they can design, get their inputs included in the design, as well as they're comfortable to use it afterwards as well. There are a few limitations of DMC. Yeah. One of the main ones is suitable for linear processes. We learn about linear processes in our control class. They are very simple, straight process. The change in output trends linearly with the change in input. But there are some processes out there which are highly nonlinear, especially in chemicals, olefins, reactors. Those are pretty nonlinear processes. It's also time consuming, as I mentioned. It can take about 6 months to an year to develop a DMC controller. The monitoring and sustainment is really the key to the success. There are several applications out there, but many turned off because there's not a proper monitoring and sustainment strategy to keep these applications running. So that's one of the key hurdles in the success of this DMC applications. Then I'll move on a little bit onto my thesis, which was control of complex processes. So we talked that DMC cannot handle nonlinear processes very well. So what to do? So that's when my advisor proposed that we do something for the complex process. And by complex processes, I mean they are highly nonlinear, multivariable process. There are multiple input and outputs to the outputs for this processes, and we focus on one area, which is reactive extrusion. This this is to reactive distillation, but just in the field of polymers, where you use the reaction to tailor the properties of a product to extruded. And what's extrusion? Extrusion is equipment. Here I show a twin screw extruder. So you have a hopper where you can put a polymer initiator, different kinds of reactants that you want, and then they go in, they melt and react with each other as the screws rotate, and then you get extruded at the end. Many applications in the field, reactive compounding and blending, uh, can be used for nylon as well as nanocomposites. For this, controlling this process, we came up with a little complicated scheme. We had three controllers really, and what you can see here is an inference model. This was the fundamental model, reactive extrusion process, highly nonlinear model, which allowed us to predict the effect of the different process variable on the product properties and make appropriate decisions based on that. So there was a customer feedback controller. So when the product goes to the customer and the customer gives us a feedback, if he's happy or not happy with the product, how do we incorporate that feedback into a control scheme? And that's where the customer feedback controller comes into the play. So what we did was we developed this scheme, and we implemented it on a pilot plant process, which was at a chemical company named DuPont, um, and we use MATLAB as well as LabVIEW interface to implement the scheme. Essentially, it was pretty successful pilot process that we developed. But in general, these complex control schemes do have limited number of applications in the industry, and one of the main reasons is the high development cost. I mean, it took me 5 years to develop this control scheme for the reactive extrusion process. It may not take that long in an industrial, still a high development cost. Um, Also, technology is not fully mature yet. There are still the research is being done how to best implement this on more complicated processes, how to build those non-linear models so that the controller is effectively using them, and so on. So more research is needed before we can say that yes, this complex control schemes have arrived and used more frequently in the chemical industry. Okay, so now let's move on to our last section here, which is optimization. This is the field I've been working on for the last few years, um, especially the real-time optimization. And as you can see, it's like the top of the pyramid where the ITO is sending targets or relying on the multivariable control, like DMC, underneath it. And what is this optimization does? Currently, for example, this graph shows we are operating at certain level, and this is where this is this is where our process is. But um, are we really making the most profit out of it or not? So how do we take the process from here to uh, the place where it's most profitable, and as well as honor all the constraints that it may encounter while it's transition from current operation to the optimum operation. And that's what the job of optimization is. I think I missed a slide here. Let's see. Oh, missed a slide here. Oh yeah, there you go. Okay, so, usually they're fundamental models of the distillation columns, reactors. I think the one I'm showing here has distillation, heat exchangers, and so on. So essentially, all the important units that are there, equipments that are there, you have to use a fundamental model for that, and then use the combined model to optimize the event. This typically there are 100,000 equations in an RTO, and you need really good solvers that can solve this big optimization problem. Usually, you will have one application per unit. There are many vendors. Some of the important ones are Romeo from Invensys, and there's Aspen One product that can do it for you. So you can build your applications in this on these platforms. These applications, if they're built properly, they can make millions of dollars for a refining unit, and so they can provide uh, um, real value to the refinery, and that's why they are being developed more and more nowadays. However, there are many challenges. You have to ensure that your RTO is doing what the economics group is expecting it to do. If it's out of line of their expectations, then usually your RTO will get turned off. You need a reliable DMC underneath it and the regulatory controllers. So being at the top of the pyramid, it really relies on the underlying control layers to be effective. As I mentioned, it needs efficient solvers since there's 100,000 equations that it needs to solve and do it in a real time. So you need good hardware to support that functionality. Also good instrumentation as well as operator acceptance. If operators don't like it, usually the idea would be turned off in DMC. So when you build it, you have to ensure that operators understand what it's doing and how it's doing. Otherwise, it gets turned off pretty soon. One final slide is on integrated process control and safety system. Process control, as I mentioned, is a key part of running a plant in a safe manner, and it becomes a part of the safety systems for the plant. So you have different layers here, as you can see. The process control usually keeps the process within the operating limits for the plant for the unit, and if it goes beyond that, then there's alarms as well as emergency shutdown systems. These are pretty standard nowadays, and there are systems like Triconex systems which can do this for you. Alright, so how is the life of a process control engineer? I'm just changing a gear before summarizing. Um, as the cartoon says, you have to do a lot of things being a process control engineer, and you have to handle many different applications that are out there. Um, and it can be a um, pretty challenging job. And if you're interested in something like this, can definitely bring value to a chemical industry or a refining plant. To summarize, um, process control schemes, as we mentioned, as we talked about, are critical to the operation units. Well, uh, any success or success of any process control scheme depend on basic regulatory controllers. Um, Still, the most common regulatory control used is the PID controller that we learn in our undergraduate class. Still, the knowledge that we get in our undergraduate is still valid and useful. Um, Multivariable controllers are used at increasing rate. They do encounter challenges, and so do RTOs, which can bring a lot of value to the unit. It's as we talked about the communication between the different layers of the advanced control pyramid are critical to the success of this thing. So with that, I'd like to take any questions that you may have from your side.
Thank you, Swapnil, for the exciting talk. Vishwanath. Uh,
Um, there are questions. A student from final year chemical engineering, Mr. Dipan Gala, will ask the first one.
Okay.
Yes, sir. I had a question regarding. I've heard of a plant in Netherlands that is fully automated. So, how far are we from fully automatic plants in other locations as well?
Typically, the newer plants that are built more recently would have more automation than the older ones. The refining in the refining field, most of the refineries have been built long time back, and they don't tend to be fully automated at this point. So anything that's new is more automated, I'd say. But it's not very common to find a fully automated plant out.
And sir, one more question. I'm planning to do a PhD in the next year. So, if as a process control PhD in a process control thing, is it more of model development and such things, or is it experimental things are also there for a process control thing?
It probably will involve both. If you're doing in a process control field, there's some people who just do a theoretical model building and development in the modeling field. But if you really want to take a job in industry, then I would recommend that you include some experimental component to it, some application, how you use your control scheme. It's definitely a plus if you do that. So you have opportunities in both areas.
Thank you, sir.
Yep.
Uh, Hello. So my name is Jane. I'm a student of Faculty of Chemical Engineering. I had a question. So can you give some brief idea about distributed control systems and why is it being widely used nowadays in streets?
Well, distributed control systems, I mean, the basic regulatory controls, as I talked about, were in the field. Now, how do we implement more complex control scheme? That's where DCS comes into the picture. and they are widely used from what I have seen. Um, TDC 3000 is one example that commonly see, and then now Honeywell has developed a platform called Experion, which is a pretty commonly used platform uh, for the DCS kind of systems. So it's being used, what I would say, and they're required nowadays. I think they're more of a rule than an exception at this point.
Thank you, sir.
Okay, thank you, Swapnil, for getting up so early for us. We are probably keeping you from getting ready for work. But I would like to propose a vote of thanks for Dr. Swapnil Garge.
Thank you for giving
Great. Thank you very much. Very insightful. Uh,
All
some of our students would like to mail you afterwards. Is that all right?
yeah.
With questions.
I will definitely mail me any questions. I will give my email address to Dr. Neeraj and or forward it to you. And then definitely send me any questions if you have any inquiries regarding what to do in process control field in terms of PhD or anything like that. Let me know, and I'll be happy to help.
Okay, great. Thank you very much. So I will let you get on with your day then. Thank you.
Thank
Bye
you.
bye.
Bye.